Hello everyone. Today let's study oscillatory motion. Oscillatory motion is the same as periodic motion, or you can say oscillatory motion is periodic motion. Periodic motion is the motion of an object that returns to its original position regularly. Let's start off by looking at the motion of an object attached to a spring. So let's consider a spring, and we have a mass attached to the spring. So I'll draw the spring system with a mass attached. Let's say the mass is m, and this is the equilibrium position of the spring. Equilibrium position is a position where the spring is neither stretched nor compressed. Let's suppose we displace the mass to a position x initially. Once we displace the mass to that position, the spring exerts a force on the mass, and that force is proportional to the position and is given by Hooke's law. So this is the initial, and then we displace it a little bit to the right. So this is our equilibrium position, and so this displacement here, this is equilibrium position is at x equals 0, and we displace it by variable x. So there is a spring force F subscript x which acts towards the equilibrium position, and this force is given by Hooke's law. And let's draw another one where the spring is compressed so that you can see the difference. I guess it's basically the same thing, but let's draw it again. This is not drawn to scale, so let's say this is x also. Actually, let me redraw that. So in this scenario here, the spring force is directed toward equilibrium position. This is relaxed. So now, as I mentioned, when the spring is stretched by stretching the mass one way or the other, there is a force that acts on the mass to push it toward equilibrium positions. And when it is compressed, the force F subscript x acts to push it back toward equilibrium position. So the force Fs is always acting opposite to the direction of the motion of the block. And this force is given by Hooke's law. So Hooke's law tells us the spring force F subscript x is equal to minus k times x, where k is the spring constant for the particular spring. The spring constant has units of newtons per meter. Fs is also called a restoring force because it is always directed opposite to the displacement of the block, and it's directed toward the equilibrium position. Let's apply Newton's second law to the spring, or to the displaced block attached to the spring. So we can say that the net force is equal to the mass of the block times its acceleration in the x direction, since we are working along the x-axis. And since the net force, or the only force present, is the restoring force, we shall say that Fs is equal to the net force, and this is therefore minus kx. So we can say minus kx is equal to ma in the x direction, and then we can write ax is equal to minus k over m times x. Let's replace k over m by omega squared, where omega is our angular frequency. So this tells us that the acceleration of the block is proportional to its position, and the direction of the acceleration is opposite to the direction of the displacement of the block from equilibrium. A system that behaves this way will exhibit what is called simple harmonic motion. So let's write that down. I'm calling the block also the mass. It's the same thing. So now let's say, suppose that the block is displaced to a position x equals a. So given the formula we have above, so we can say that from our acceleration formula above, then the initial acceleration of the block would be given by minus ka over m. And then we can say that when it passes through the equilibrium position at x equals 0, its acceleration a subscript x will be equal to 0. We can say then at x equals minus a, its acceleration will be a equals kx, ka over m. That is a positive ka over m. And so the block oscillates between the turning points x equals plus minus a. Let's explore the details of oscillatory or simple harmonic motion next.